Hello everyone, welcome to another class, and today we'll be dealing with electromagnetic induction. So please pay rapt attention as we have a deep dive into this. Like I said, today we are taking a lecture on electromagnetic induction, part 1. And so in that, we'll have we'll talk about the following things. We hope we're able to finish up with the part 1. So let's start by talking about the induced current. Induced current. What is induced current? Induced current. Okay, let me explain by starting with this. Electromagnetic induction is the production of electric current or voltage in a conductor whenever there is a relative motion between the conductor and a magnetic field or a magnet. So, you see, that's the definition of electromagnetic induction. So, this induced current, the current produced whenever, you can give it that definition, whenever there is a relative motion between the conductor and a magnet, is called induced current. So it's just, a definition that is related to the definition of electromagnetic induction. So let's talk about a few points about the induced current. Oh no, let's make it the induced current or EMF. So both the induced current and the induced EMF depend. It depends on for one, the speed of motion of the magnet. So here you have the faster the speed of magnet, the larger the induced current. The B part you have also depends on the number of turns of the coil. Also depends on the presence of a soft iron core inside the coil. So I'm going to draw so two diagrams. I'm going to draw two diagrams, and we'll use it to talk about how the induced current operates. So I'm going to draw this one first, where I draw a magnet. This is the South Pole. This is the North Pole. So this is the coil around it, and then it's connected to a wire where you have the galvanometer, and this is the direction of the galvanometer is facing, telling you that current is flowing like this. So if current is flowing like that, in this case, you have okay. Current is okay. This current is flowing like that. Okay. We now have the magnet. This magnet, you are pushing it inwards. It's a magnet plunged into coil. Yeah, so then in the coil, you have the induced field. In the coil, you have the induced field moving upwards. Let me use another color for that. Let me use green. So it's going up. Or should I use red? So that's how it's moving like that. So as the coil is rotating, as that's the motion of the coil. So the motion of the coil is like that. That's how the coil is rotating, like that. So then there is another thing called the induced field inside the coil is now moving in this direction. Induced. So a lot of things are happening. Induced field inside coil is moving like that. So we already have current. You can see that current in the wire is moving. See it like this. Current is moving in the wire. That's this one. You see current motion. So induced field inside the coil is like that. Then this particular one, black, is the motion of the magnet. We're moving it inwards. Magnets plugged into So in this case, it's into. So this is one case. Then let's draw another corresponding case down here, where you have the magnet, south, north, you have your coil, and this time current is like this. So we have current moving like this now. So current is moving. This is use green. Current motion is like this. Then you have this time around it's going to be opposite. The induced field will go like this too. And the motion of the coil this time is downwards. So see it. And the one above is going up. Then this time around, the magnet is pulled out. It's being pulled out of coil. Magnet in this case, magnet is pulled out. So let's now discuss some of these points we have made with the diagram. So let me say the coil is wound. That is the past tense of wind. When you wind something, that's the past tense of wind. So and that's like rolling it. So the coil is wound on a steel ring. When the switch is closed, a deflection will be obtained on the galvanometer. Galvanometer is that guy that has the arrow sign. So the point we had made before. Oh. This is not the point I'm trying to make. Excuse me, please. Sorry. Let me quickly just delete this. Well, the point I'm trying to make is the direction of the induced current reverses when the direction of motion of the magnet or coil is reversed. Are you seeing that? So the direction of the induced current, if you look at the above, when we're told that when the direction of the motion of magnet is reversed. Now, in this first case, the motion of the magnet was inwards, while in this case, the motion was outwards. You can see that in both cases, the direction of the induced current are opposite to each other. You see the direction of the opposite. Because in the first case, the induced current, the induced field was moving like this. See why it was moving? You can see that. While in the other case, the induced field is moving in the opposite direction. So just keep that in mind. That's the point that I was trying to establish. Let's now talk more by saying current. Current will flow in the galvanometer. Current will flow current will flow in the galvanometer whenever there is relative motion between the coil and the magnet. There is such a relative motion when the magnet moves towards or away from the coil. And when the magnet is stationary, the coil is moved. So that is the concept. We move straight to the next part. This has to do with the laws of electromagnetic induction. Laws of electromagnetic induction. There are two laws. So we start with Faraday's law of electromagnetic induction. And Faraday's law of electromagnetic induction states that whenever there is a change in the magnetic lines of force, whenever there's a change in the magnetic lines of force, okay, let me remove this bracket. Go. EMF is induced. Or let's say electromotive force. Let me write it in full. So whenever there is a change in the magnetic lines of force, an electromotive force, EMF, is induced, the strength of which is proportional to the rate of change of the flux linked with the circuit. Please take note of that. So, let me make the following points. The magnetic flux or field lines linking a coil depends on, number one, the magnetic field strength. Two, the number of turns of the coil. The magnetic field strength, the number of turns of the coil. And number three, the area of each turn. Now, to obtain a large induced EMF, the idea is to move. So to obtain a large induced EMF, move at a high speed. Move at a high speed across a strong magnetic field. Move so For EMF to be produced, the coil has to be moved at a high speed. This will have more number of turns across the strong magnetic field. Let's now quickly go to Lenz's law. Electromagnetic induction. That particular one states that the induced EMF is in such a direction as to oppose in such a direction. Hold on for a bit. In this EMF is such a direction as to oppose. Okay. As to oppose the motion or change producing it. So let me put this as let me name this guy induced EMF. So let's say induced EMF. Call this one induced EMF too. So the Lenz law states that the induced EMF is in such a direction as to oppose the motion or change producing it. First and foremost, see the motion of the magnet is kind of moving like this. See the induced EMF like this. Here, the motion of the magnet is like this, and the induced EMF is like this. So opposite relationship. So states that the EMF is in such a direction as to oppose the motion or change producing it. So basically, the Lenz law gives you the direction of the induced EMF of induced current. I'm going to now talk about an induction coil. An induction coil. So, induction coil. This is an electrical device that is capable of producing a very high intermittent EMF by electromagnetic induction. Capable of producing a very high intermittent EMF by electromagnetic induction from a low voltage DC, a low voltage DC or low voltage direct current. Let's put that. So please keep that definition in mind. Read it or reread it. That's your role and responsibility. E.g., example is a battery. I mean, when we say low, an example of that low voltage DC is battery. So this point is not low voltage DC battery. So let's go on. So the induction coil consists of a primary coil. The primary coil is made up of a few turns of thick copper wire wound, and this wound is like past tense of wound on a laminated soft iron core. Now, please listen attentively at this junction. In the induction coil, the function, the lamination, this thing comes out in multiple choice or OBJ. The lamination of the core is to reduce loss of energy due to eddy current. So please take note of that point. The lamination of the coil is to reduce loss of energy due to what? Eddy current. The lamination of the coil is to reduce loss of energy due to eddy current. So now the other, so we said the induction coil consists of that. So the other thing it consists of is a secondary coil. So this overlaps the primary coil. It's an assignment. I need to go to your materials and give me a brief explanation of eddy current. I'm deliberately giving you that. The secondary coil overlaps the primary coil, and it is made of a large number of turns of insulated thin copper wire. The ends of this coil are connected to an adjustable spark gap created by two adjustable brass rods. So, made up of the primary coil, secondary coil. Then another thing it is made up of is that in front of the soft iron core of the primary coil is a make and break device consisting of soft iron armature carried on a light brass spring to which is attached a platinum contact with adjustable screw front of the iron core to make a break. So it has an armature. So the primary circuit is completed. So these are just important points. From this contact to a key and battery, which provide the current. So a good point is the induction coil is commonly used in motor car ignition, system, and in the operation of X-ray tubes. So yeah, these are the notes for today, and I hope you just take them down, reread them, revise them, and I hope you are also doing your own personal revisions for your exam. So this is the induced current, electromagnetic induction part 1, and I'll see you in my next class.